And this talk is not about port Hamiltonian systems, it's not about energy, it's not about physics, but it's about control to some extent. It is about control of diffeomorphisms, as Agrachev would put it in one of his famous papers on this topic. And it's about learning from data, learning diffeomorphisms from data, which is a topic that perhaps you'll hear more about in the next talks, in the talks to come. I also think this topic has a number of tools, geometric tools and structure preserving tools that are useful, perhaps not only in the field of shape analysis, which is what I will discuss today. Okay, the outline is as follows. I will start with the motivation. Why do we want to look at data in the sense of shapes, as shapes? And when is this appropriate? And then I will say some brief introduction of how this is done, at least in the ways I'm familiar with. And I will talk about the approach based on the square root velocity map and the Q transform to compute distances between shapes. And then I will address the main problem that I'm discussing today, which is the reparametrization of curves and surfaces. How to find the optimal reparametrizations of surface and surface and curves. And then I will give you some examples and some theoretical results, if the time allows me. Okay, let's start with the motivation. So when we talk about shapes, we can have in mind the following idea. We have images of objects, and we represent them with their contours. And then the contours are what is the shape is about. And then, so this is one possible way of thinking. And these curves, they are independent. They are the shape. They are independent of the parametrization of the curve. They are unparametrized curves. Another example is this example here, where the shapes are surfaces. And here you see you have different shapes, and you want to map them one into the other, or transform them one shape into the other. For example, a horse into a cow, a hand which is open with a hand which is not open, and different shapes. So also in this case, if you want to compute distances in between such surfaces, then it is perhaps a good idea to look at them independently of their parametrization. A completely different examples that I've been considering and working a little bit with is this of virtual characters and skeletal animation, or activity recognition. So here, what you want to do is to create animations in computer games, for example. And then what you do, you have some data which represents motions of several types, and you want to blend this data, manipulate this data in order to create new animations. Or another application is the case when you want to recognize the type of activity that is done. So you have to, first of all, digitalize the data. And what happens is that the data is time dependent, is a time curve, and the configuration manifold is J here, is given by a number of copies of SO3, so a bunch of rotation matrices. So the data is obtained by motion capturing. So you have people moving, and immediately you can digitalize that by computer graphic facilities. And then you can manipulate this data, or you can recognize this data. So here, at the beginning, what we did was to look at, what you can do, or what you realize is that it's a useful thing to look at the data, especially if you want to compare animations, or if you want to compare activities. It's useful to look at the data independently of the speed. And then you do what is called dynamic time warping, and you try to align these curves in an appropriate way. This means essentially that you have to look at them independently of their parametrization. But another aspect of this is the geometry, which means that you can gain something by looking at this curve or taking into account the fact that the curves are evolving on a Lie group. So here it's a classification problem. We have running, walking, and jumping animations, and we want to classify them. And this is a quite nice result. So it clusters. This picture shows that you cluster pretty well the jumping animations here, the walking animations up here, and the running animations down here. So they are very well separated. And how do you achieve? How is this achieved? So this is achieved by using shapes. So by looking at curves as unparameterized curves, and then, but also using the geometry, using the fact that you have curves on SO3 and taking that into account. So this is very much in the spirit of structure preservation. And I don't think it would be possible to obtain similar results avoiding or ignoring one of the two factors. The problem with this is that computing this reparametrization, or taking into account that curves are reparametrization invariant, it's quite a costly matter. It leads to costly optimization algorithms. So my talk is an effort towards getting algorithms that are cheaper to compute these reparametrizations. Okay, let me then introduce the techniques behind this. And so we are looking at shapes as unparameterized curves or surfaces, and we need to take into consideration problems where this makes sense. So it's not every application where this is a good idea, but I gave you 3 examples where this might be useful. Okay? So not always it's important to look at this reparametrization invariant thing. So we are going to consider shapes or describe shapes as by starting first from the so-called pre-shape space. And for the case of curves, we consider the space of immersions. So we take C-infinity curves with the non-vanishing derivative. This condition of being non-vanishing, the derivative being not vanishing, makes this P space into an infinite dimensional manifold, Riemannian manifold, in fact. So this is important. This will play a role later on. We cannot work with this P space as a vector space, but we have to consider the geometric properties. And we say that the 2 curves are equivalent if they differ only from the parametrization. So if one is the reparametrization of the other. And this essentially describes the fact that they are a shape. So the shape space is simply the quotient space of the space P that I introduced before with the diffeomorphism group, with all the parametrizations, which are then a group, and it's the diffeomorphism group. In particular, is the group of orientation preserving diffeomorphism. Again, an infinite dimensional manifold, an infinite dimensional Lie group. So we are dealing with infinite dimensional manifolds and infinite dimensional Lie groups. Okay, so useful, you must agree, is to have a notion of distance between shapes or between curves. If we want to compare them, we're going to need some sort of notion of distance. And the way one describes this is, or defines this, is by starting with the distance on the pre-shape space, on the space of immersions in my example, in my slide from before. And then by taking the infimum over all possible reparametrization. So here is the definition, the typical definition of distance for between two equivalence classes, two shapes. Take the infimum over all diffeomorphism, orientation preserving, of the distance of the parametrized curves C0 and C1 reparametrized. Turns out that, I'm reparametrizing only one of these two curves here in all possible ways. And turns out that this is possible if this dp is of an appropriate type. It's the reparametrization invariant, which means that it's in the distance between C1 and C2 or C0 and C1 is independent on, is the same if I reparametrize both C0 and C1 with the same reparametrization. Okay, so how do you design a notion of distance on the pre-shaped space, on the parameterized curves or parameterized surfaces? You go about and consider a Riemannian metric on the same space. Turns out that, for example, the obvious choice, the L2 metric, is not a good choice because it leads to zero distance in the shape when you pass to the quotient. So, so this is so you need to come up with something smarter, essentially, something better. But you can do it. There are several ways to do it, and here I show something. So you take your Riemannian metric, and then the distance between the curves in the parameterized space is simply the length of the geodesic that the Riemannian metric is giving you. And what is a geodesic? So these pictures, they give you examples of geodesics. Sorry. So geodesic from the curve, which is a straight line in this picture, to this curve here, is simply an optimal deformation. Okay? And this optimal deformation is defined by the way you define, or you choose this Riemannian metric. And as you can see, the optimal deformation doesn't change if you reparametrize the curve. You can see here I have equidistant points on this curve and also here, but then I reparametrize the curve, I move the points in a different way, similar here, but the same reparametrization, and the deformation doesn't change. But if I change this one way or this one in another way with two different, then the deformation changes. Okay? Okay, so an alternative way, instead of cooking up your Riemannian metric on the space P, an alternative way, which is a bit algorithmic and relatively easy to use, is by first transforming the curves with an appropriate transformation, and then using a familiar notion of distance, which is the L2 distance. And this can be done with two transformations. For example, for the curves, you can do it with something which is called the square root velocity map, which is simply take the curve, take the derivative with respect to the parameter, and scale it with this norm. or with the so-called Q transform, where you simply scale the curve. You take your curve and you scale it by this thing here, which depends on the derivative. So they are the distances you get are simply the L2 distance of the transformed curves. Okay? And they are well-defined notions of distances. But why is this these are interesting transformations? The reason is that the dp here, the distance that you get, is reparametrization invariant. And this is due to the fact that or corresponds to the fact that the two transformations here, Q, that define Q, are so-called reparametrization equivariant. So if I reparametrize the curve and then transform it, it's the same as I first transform the curve and then reparametrize it, apart from the scaling here, apart from a scaling factor. Okay? So this is crucial to get the reparametrization invariant of dp, which then boils down to a good notion of distance in the shape when I go to the quotient. Okay, so since I have this setting here, and I want to use this kind of definition for my distance, then to find the optimal parametrization and to find the distance on the shape space, I will have to solve an optimization problem of this type here. So this is the reformulation. This is simply a reformulation by using the facts that I've discussed in the previous slide, reformulation of the distance on the shape space. Okay? So in other words, I have a cost function here, which depends just on the L2 metric. Q0 and Q1 here are the transformed curves. And I'm going to have to solve an optimization problem on the diffeomorphism group. Again, infinite dimensional Lie groups. So I'll have to discretize somehow. I'll have to make a finite model for this, something that I can compute. And our proposal is to consider a basis of the tangent space at identity of the diffeomorphism group. Start from there, and then make composition of elementary diffeomorphisms. So I will take a linear combination of this basis of the diffeomorphism group. So essentially, I'm selecting a finite dimensional subspace of the tangent space. And I pick vector fields in there, and I add to them simply the identity. This is, if you think about it, is like the Euler method. It's like you have a vector field, you have a differential equation that is defined by that vector field, and you apply the Euler method to that. That gives you the diffeomorphism. Is this a diffeomorphism? Turns out that the answer is yes. Here is, I will get back to this later, but let me give you just an appetizer, sort of. So we can show that finite composition of diffeomorphism of this type, so the identity plus a vector field, which is one Lipschitz, I will explain why we want one Lipschitz later on, can be used to describe the whole group of diffeomorphisms. I have both surfaces and curves. In fact, I do this for surfaces, because for the curves, there are many other methods. But for example, the dynamic programming for curves is okay, but if you go to surfaces, it becomes very complicated and costly. Okay, so we will distinguish the case, in fact, of diffeomorphism fixing the boundary and diffeomorphisms on a cube, because are those that are the applications that we have been looking at. But yeah. Okay, let me show you some results. Okay, let me go back just a second. I call this deep learning of diffeomorphisms. Why is that? Because in fact, one such map is like a layer of a ResNet neural network. So the composition here, I have L layers, L composition of diffeomorphisms. So I can in fact code up this with PyTorch. So just to demystify neural network. To me, it's an important exercise. All right. Okay, so let me start with considering basis functions for the case of curves. Here are three options: Fourier basis, Jacobi polynomials, or the Palais basis, which is related to the Fourier basis, but it is scaled differently. For the surfaces, you can take tensor products of the Fourier basis, for example. This is what we have been using for our experiments. And you can bound Lipschitz constants. You can characterize the Lipschitz constants of these vector fields. So these, these are just components of the vector fields. The vector fields will have two such components, so you will have to pick two of these. Okay, here it's one example. This is a simple example. I have two curves. One is the parametrization of the other, and you can see that from the way that these dots are distributed on the curves. So in the first curve, they are sort of equidistributed. In the second curve, I've reparametrized it, and the dots are distributed differently. Okay? So what I have to do is, in this experiment, is simply to reproduce the reparametrization of these two curves. Finding the optimal reparametrization means just reproducing that. So it's a simple experiment, but it's good for testing our code. If we use only one layer, and five basis functions, I don't remember which basis we have used here, then you see that the approximation you get is given here, and is not perfect. It's still kind of working, but not perfect. And this is the iteration of the gradient, the iterations of the gradient descent algorithm for solving the problem. And you see that the error goes down, but this is but it starts flattening out. Okay. If you use several layers, this is what you get. You get a much better approximation and a much better descent in the gradient descent. Okay, so it works. It's good. Didn't do this without any result. Here is a more systematic experiment where, in the first picture here, what we plot the error against the number of layers versus the number of layers that we use in the method. And the different curves are for different number of basis functions. So essentially, you get convergence if you increase the number of basis functions and increase the number of layers. But if you increase the number of layers and you have only one basis functions, you are not doing very well. So in some sense, it flattens out. But if you just use a fixed number of basis functions. In the second experiment, instead, I did the experiment the other way around. We did, Jürgen did, my student. And here we have the error towards the number, against the number of functions per layer. And here one layer, two layers, and several layers on the way. Here is an example with surfaces, same example as in the previous case. And so we have two surfaces, just one is the reparametrization of the other, and we have to find the reparametrization. And here is the reparametrization, which is given, and the iterations of gradient descent. And finally, my final example is morphing of surfaces which are obtained from the MNIST data set. So we have digits. We have made surfaces by interpolation. So these are digital images. So we interpolate with bicubic interpolation to make them into surfaces. And then we morph, or we transform the number 1 into the number 2 by computing a diffeomorphism. So the number 2 in the middle here is just the composition of this surface with the diffeomorphism here. So if you compute the distance in between between the number 1 and the number 2 without reparametrizing, you get this error here. And after reparametrization, after finding the optimal reparametrization, you get this error here. Okay, so now I want to say something more. I'm not sure about my time. How it's... Okay. All right. Okay, so now I want to say something about this expressivity result, okay, or this approximation capability that we and how we do it. So let me go back here. We distinguish two cases. The first case is the case of diffeomorphisms that are fixed in the boundary on a compact set contained in RD, and the second case is the case of a cube. Okay, okay, let me look at the first case. We are looking at diffeomorphisms that are the identity on the boundary. Okay, so it's a little bit restrictive, not extremely restrictive. We have made experiments with these diffeomorphisms. Still quite, they work, even in the cases that I've shown before, but still it's not so nice to have this restriction. Anyway, if you take the tangent space at the identity of these diffeomorphisms, then these are C-infinity curves which vanish on the boundary. And it turns out you can prove that there is a global chart for the diffeomorphism group. So this is the tangent space. There is a map K, which is a global chart. Only one chart. So you can describe the whole manifold with one chart. And this global chart is the inverse of the Euler method. The inverse of the Euler method. So you take your diffeomorphism, and this subtract the identity. Then good news, then we should be able to represent diffeomorphisms of this type by just looking at vector fields and adding the identity. Any vector fields, huh? But the problem is that it's not any vector fields, it's just those that just those appropriate ones. So it's quite difficult to describe the counter image of this chart map, or the image that then is the place where you want to pick your diffeomorphisms from. So it's difficult to describe. There is this fact that we are going to restrict to a finite dimensional subspace of the Lie algebra and not the whole Lie algebra. And of course, not all diffeomorphisms of interest are of this type. But anyway, in the 1D case for curves, this is quite simple. So to describe the image of this chart map is very simple. You can just take the derivative and take vector fields such that this condition is satisfied. And this will, so monotonically increasing vector fields. But in several dimensions, this is different. So you have to have an escamotage or do something different. And what you do is you are considering this set U1 here of vector fields which have Lipschitz constant less than 1. And turns out that this set is a neighbor of the origin in the tangent space, open neighbor. And that you can prove that, of course, it's not too difficult to prove that if you take any such vector field and you add the identity, then you end up into the diffeomorphism group. So if you take the vector field F within this space, within U1, and you add the identity, then you get something in the diffeomorphism group. Now, this fact that it's a zero neighborhood of the tangent space and that it's contained in the diffeomorphism group is sufficient to have the following, that if you compose a finite number of diffeomorphisms of this type, essentially you can get the whole diffeomorphism group back. When it comes to the cube, things are slightly different, but not that different. So the result is rather similar. So I don't want to go through it again. So what you do, in fact, also in this case, you are reproducing not the whole diffeomorphism group, but the connected component of the identity, and that's what you want. So it's the deformations of the identity. And similarly, in this case. Okay, this is a result which is similar to a result of Agrachev on this paper with Caponigro, if I recall correctly, on controllability of diffeomorphisms. But those techniques are quite different, are based on geometric control, and these are ideas based on infinite dimensional Lie group theory. Yeah. We also derived bounds both for the norms and for the Lipschitz constants of the composition of diffeomorphisms. And these are useful because normally you would like to be sure that you have some sort of boundedness of the network. There are these problems of exploding gradients in neural networks, and these sort of bounds are things that are useful. And we have derived also similar bounds for higher order differentials. They are cool bounds, very nice recursive formulas, a little bit complicated perhaps, but the problem is that probably are quite pessimistic. So, but we are not quite sure how if it is possible to do it differently. All right, this was the end of my talk, and I leave you with a bunch of references, and I thank you very much for your attention. I wouldn't know the answer to that, but I think it's omega is important. The topological properties of omega are important. I wouldn't from discussing with my co-authors who are more expert than me in this, I wouldn't imagine that changing the omega makes it just the same. So if you have your favorite omega, then you're bound to have a job to do. What do you say? If you understand the topology.
If you fully understand the topology of your omega, then it should be possible, because then you understand the Lie algebra and you understand where the fundamental curves are, and then operate on that level too.
I think it's certainly important, right? If you want to do applications which are not just squares and intervals. So it's I'm not sure about how easy it is. I think that normally one looks at a compact set. That's it. No, with not much description of what it is, with no much constraints or any features described.
But I guess at least for the circle, should
the circle would be good. Yeah, the disk, a disk. Yeah.
Oh, a disk.
Disk is included. Yeah.
Okay, thank you. Is there some other question? Oh, okay.
I don't think I need this, but well, anyway. So when you want to compute the diffeomorphism linking to shapes, so what is the input information? Is it a point cloud on shape 1 and on shape 2? And then your optimization procedure finally yields this diffeomorphism in this parametrized form. Do you start from point clouds?
They are not exactly point clouds. If you look at the MNIST data set, they are images. So they are points, pixels, but not clouds necessarily. Mm-hmm. And then we make the surfaces ourselves, or we interpolate. But for the curves, it's a sequence of points. Mm-hmm. Yeah. So it depends, I think, on the application, how your data is given. Mm-hmm. I guess these 3D images perhaps are point clouds, like you say.
Mm-hmm. Okay, so then the input is essentially of point cloud type.
Yeah, I would agree to that, but I figure that the point clouds, they don't have any ordering, while the images, they would have an ordering, if you understand my point.
Pixel image, then you just use lexicographic ordering and say, my diffeomorphism is supposed to map this pixel to that one.
Yeah, and also you know what are the neighbors, right? And the point cloud could be, okay. Mm-hmm. If your surface is very complicated, then you say these two are neighbors, I have to join them, but they are not, right?
Uh-huh. All right. Uh-huh. So this is another challenge.
I guess so.
Cloud case.
I guess so.
Mm-hmm. Okay, thank you.
So is there some other question? So in this case, I close the first morning session. Thank you very much again.